We're about to have the Oded Schramm Lecture, which is jointly sponsored by the Bernoulli Society and the IMS. It's in memory of Oded Schramm, who was one of the great mathematicians that died, unfortunately, in a hiking accident about a little over 10 years ago. He contributed in many areas, circle packing, I was going to get to that, but most famously is known for his contributions to conformal invariance, including the process that now goes under the name Schramm-Loevner evolution. I can't think of a more fitting person to actually give the Schramm lecture than our lecturer today, Stanislav Smirnov. He did his undergraduate work in St. Petersburg, got his PhD under the direction of Nick Makarov at Caltech. I believe I first met him when he was at Royal Institute of Technology in Sweden, when stuff in SLE was first coming out, and he was a very interested postdoc, I would say, at the time, trying to learn what he could. Little did we know what he was actually going to do in the next few years. In many ways, he is the one who completed what Oded started. Oded showed what the scaling limit of percolation should be, and Stas is the one who was able to establish it. He did also very non-trivial work on the self-avoiding walk, and also did excessive, beautiful work on the easing model and related processes. And overall, he's done what sort of developed the area that now goes under the name discrete holomorphicity, and there are many people who are pursuing that today, all based on the start of Stas. Just to mention a couple of his prizes, the first one I'll actually mention that he won the Salem Prize. I mention that because he was actually a joint winner with Oded Schramm for this prize that year. He's also was a Clay Research Award, the Rollo Davidson Award, and probably what he's most known for in 2010 is the Fields Medal. Without further ado, I would like to call Stas up and present him with the certificate for this.
Well,
I think I have a picture here.
Oh, it's upside down. Oh. Thank you.
And his talk on 2D percolation revisited.
Thank you, Greg. It's certainly a great honor to give an Oded Schramm lecture. Albeit a sad one, he really parted very early with us. And before I want to say a few words. There were two more colleagues who contribute a lot to percolation who just left us this year. It's Harry Keston, his name will be mentioned more than one time in this talk, and Vladas Sidarevičius, who also left very young as Oded Schramm did. But let me pass to Oded Schramm and say a few words about him. As Greg remembers, when I came to Stockholm, I was actually doing before that dynamical systems, and before that I was doing complex analysis. And at that time, I will come later to that, Lennart Carlesson and Peter Jones, my great friends and mentors and colleagues, were very much excited about percolation. And the first thing I tried to do is to understand what physicists were doing with percolation. And I remember Kari Astava came from Helsinki for I think 2 weeks, and our plan was to read a 4-page paper by Bertrand Duplantier. And 3 days we managed to do 3 paragraphs, and then we got stuck. And then next morning the first paper of Euler, Schramm and Werner series appeared, so we happily spent the last 10 days of the 2 weeks understanding that paper, which was much more exciting thing. And little did I know how much progress it will eventually lead to. And then in Strasbourg I saw Oded and Greg and Wendelin at a conference, which was actually a very interesting experience when you change the area. I arrived together with Lennart Carlesson, who was sitting in the last row, and I just realized I was telling Lennart, look, I read at least one paper from every person in the room, but I don't know anyone by face. Let's try guessing game who is who. He said, yes, let's try. I also don't know, have read all the papers, don't know them. And then he said, well, I remember 20 years ago when I came to dynamical systems, I had exactly the same experience. I came to conference and I was trying to guess who is Dennis Sullivan, who is Michel Feigenbaum. And now we were trying to, actually we managed to guess that, we managed to guess Greg, we didn't guess Wendell and Werner because he looked much younger, we thought him a student. So what I remember about Adet, that he was always had this sort of happy outlook at life, and you see there are these two pictures from his last few months smiling. One is at a conference, I think, in Canada, and the other one is at a Berwolfach meeting, and the one at the Berwolfach meeting is after Nick Makarov, my advisor, just said, well, you see, he's the only one holding a glass of white wine, not the first one. He said that the SLE is the most idiotic thing he has ever seen in his life, Schramm-Leuven revolution. And then Schramm looked at him and said, but, for example, we described the scaling limit of percolation and turned to me for some support, and Nick said, percolation, well, that's the most ridiculous model. Why just toss coins independently? So Audit was taking, but Nick, if you know Nick, he likes to say things in jest, and you see everyone is appreciating this. Well, Gabor Petty is being a bit young, he's a bit scared of Nick saying these things and doesn't know how to take it seriously or not, but Adet was very, very happy, and actually what Nick meant at the time is that it's a very nice object, but it doesn't help to understand the conformal field theory, what physicists were doing. As I said, we were trying to understand, everyone in that room tried to understand for a very long time what they are doing. In the end, I can't say that we really did. On the other hand, as a sweet revenge, now they're trying to understand what we are doing, and they're actually having easier time of that. So I decided to speak about percolation, and so who knows what percolation is in this room? Can you raise your hand? Okay. Well, it's actually a difficult thing because some people know it better than I do. Some only have maybe heard the definition. Okay, who has a good knowledge of what percolation is? Oh, well, yeah, it's still a few hands. So I will try to say a few things, and there will be two parts of the talk. A bit about percolation from 60s to 80s, so I would say about pre-Schramm mathematics. And I will speak about the percolation in the plane, and then I will speak, the second part is about post-Schramm. So the definition, well, it's perhaps the simplest model. So it's traditionally said that it was introduced by Broadbent and Hammersley in 1957. And they asked a question, so they were trying to model how something is seeping through a porous medium, so they were actually speaking about filters in the gas masks, or you can imagine it as a city. So suppose you have a rectangular city, so it's a big piece of Manhattan, and suppose that there are some roadworks, and independently each road between two intersections is open with probability p and closed with probability 1 minus p. So that's called Bernoulli percolation. It's the simplest model. Ising model was introduced long before. This is much simpler because there is no interaction whatsoever. Of course, since there is no interaction, there is no sense to speak about spin correlations because everything is decorrelated completely, and it's sort of a perfect example for the previous talk of FKG and all such events. But there are non-trivial events, and those are the crossing events. So, for example, can you drive from top of the city to the bottom of the city? So if P is large, it's clear that there are many roads are open. Usually you can drive. Probability is not 1 because with very, very small chance, all the roads are still closed, even if probability of a single road being closed is 1 in a million. If there are a million of them with probability 1 in a million to the power 1 million, all of them will be closed and you cannot drive. But that's very unlikely. On the other hand, with probability of closures is high, you cannot get through. And actually, you see it in real life that when the traffic jams start, it's sort of at one point you can drive, and then it goes to a standstill. And this was also used for many other problems, usually with more general graphs, not necessarily planar, but for example, spread of epidemics. It makes sense for planar. It made sense with planar graphs before air travel. Now, of course, the graph is more complicated. Person can fly from JFK to Paris and spread the disease overnight. But this is basically what is clear from this picture, that when you change this P, the properties, they drastically change. And you can play this game with like bond percolation like here, or you can play with plackets. It's similar for the square lattice. And if you analyze this picture, you see that here there will be some jump at 0.59 approximately, here approximately at 1/2. So you see that it looks like there is a phase transition behavior. I bet the phase transition is at different points, and that's what bit running ahead a bit fast. That's sort of logical from a physics point of view, like different liquids, they are boiling at different temperatures, and it's very rare that the temperatures are some rational numbers, like water boils at 100 degrees only because that's the definition of 100. 100 is such a number that water boils at this number. It's usually it's some transcendental number, but the properties of boiling liquids are the same the way they boil. So here you also expect the same behavior near this phase transition. What actually is plotted on this graph, you take different sizes of the box and you plot the probability that you can drive from top to the bottom of the city. It's clear that for any finite box, it's a polynomial in P, because all the events are monomials, all simple events are monomials in P, so you add them. So if the box is 100 by 100, then there are approximately 20,000 edges, so it will be a polynomial of the degree 20,000. And clearly it will be an increasing one. But as Weierstrass theorem shows, polynomials can approximate anything, and what happens is that as degree gets higher, the polynomial approximates more and more the function with a jump at one point. So you don't have a phase transition in a finite size of the city, but you get closer and closer, you get it in the limit you just get function with a jump. In principle, it goes so fast, we will see a short proof later, that already in the size 100 by 100, you essentially see like a jump. There is another way to look at it. So you can look what is the probability to drive not from north to south of Manhattan, but to escape from Manhattan. You started near Penn Station and you try to drive out of infinite Manhattan. Then if you plot to distance r, again, you get smooth graphs. But if you plot probability that you are able to drive to infinity, then it's exactly 0 for small values of p, and then you get some smooth function, so you get a phase transition. But again, you need infinite size at this. And PC depends on the lattice, so square lattice is really sort of, for side percolation, it's really canonical physical example, because there is no specific nice meaning for the PC, but there are PCs, we'll come later to that, which can be calculated, 0.5 for bonds on square lattice and sides on triangular, and sometimes there are weird numbers like twice sine pi over 18. Now, why this critical regime at PC is important? If we see that if we are supercritical, then we can drive everywhere. If we're subcritical, we are stuck in traffic jam, we cannot leave the city. And the critical regime is very unstable and very rare. Well, in real life, you don't have constant P over, well, for example, if we go 2 talks back and we start burning forests. So if the forest doesn't burn very fast, it's described by not Kardar, Parisi, Zhang, but rather by this, and Knizhnik, Polyakov, Zamolodchikov was mentioned. So if you burn a forest, P here, it's sort of some function, for example, of the temperature and how close are trees to each other. So it's probability that fire jumps to the next tree. It's not constant throughout the forest. And the region where P is large will burn out completely. The region where P is small, the fire will stop immediately. And if fire burns through the forest, large P regions burn, small P regions don't burn, so the fire stops exactly in between in the regions where P is almost critical. So that's why the critical regime is important, why you see it in real life, and actually it's a theorem of Pierre Nolan, so that in this model you can really observe the critical percolation. So there is actually a mathematical theorem now. So those are some physics pictures. So this is a model of erosion, a computer model. If you really observe erosion in the real life, usually it would take a lot of time. Sometimes it can be like in Jeremy's talk, but that usually happens in the presence of gravity or some other sort of one-directional force. But if you really like burning forest without a wind, then or you do erosion, you get percolation type clusters. This is acid eating up some aluminum film, and this it's kind of funny. You see that the subscript is in Russian, so it's aggregates of gold, and I copied this picture from a popular book about percolation I read as a high school student. But it was written by physicists, so it had mentions of Keston's theorem, a couple other things. No, it was before the Keston's theorem. It's like 78 or something, yeah. So it's so even like I realized it only last year that actually I read this book, moving my things from one bookcase to another. I found that book, and it's actually a very nice one because it has lots of mathematical conjectures, which were conjectures at the time and no longer are. And those are actual pictures taken with an electronic microscope, and you have things which look like percolation clusters. So what makes two dimensions so special that people can prove theorems there, whereas we still are at a loss what to do with 3 dimensions? It's a planar duality, well, this is a model which makes for a nicer picture. So it's a side percolation on triangular lattice, or equivalently, we pass to a dual graph, it's a placket percolation on hexagonal lattice. We toss a coin, and since I was at Metacle Fleur at the time, it's a 10 kroner coin, and you cover white or yellow, or blue or yellow, as again it was Metacle Fleur, and you take p equal 1/2. In a second we'll see why it is critical. And there is always, in every of these pictures, there is either a top-bottom open crossing or left-right closed crossing. So, for example, here there is a white crossing from top to bottom. Now, here, can you see whether there is a crossing here or not? Well, that's a difficult problem. Here it's easy to see. Here it's difficult. Well, I will explain later why it is. So here there is a top-bottom crossing, so now I put blue water on top so it seeped through. Here it seeps only to here, and the reason is that there will be a yellow obstruction which sort of prevents water from seeping through. So there is always a top-bottom blue crossing or left-right yellow crossing. And that strongly indicates that PC should be equal to 1/2. Why so? Because probability at P to have a blue crossing top-bottom is exactly 1 minus probability to have left-right crossing in yellow, but yellow has probability 1 minus p. So you get this identity, and if you use some symmetric shape, for example, a square for square lattice or a rhombus for triangular lattice, so you can take square for triangular lattice, but you should rotate it 15 degrees. If you take p equal 1/2 here and here, the indices will be 1/2, and also the shape is symmetric, so these two probabilities will be the same. So you get that probability is equal 1 minus itself, so it's equal to 1/2. So you see immediately that if you have self-duality like for this lattice, that at p equal 1/2 something interesting happens. So there the probability for symmetric shape is non-trivial. But it took a lot of many smart people to actually prove that it means that there is a phase transition. So for physicists, it's immediately clear that there is a phase transition. But the mathematical proof, it went many steps. And if you look, so there are 2 main mathematical books, one by Jeffrey Grimmett, one by Harry Keston. If you look at the proof of this thing, it occupies two chapters, and it's well over 70 pages. It's difficult both ideologically and conceptually, and also on the other hand technically. So what interesting happened that a number of people were doing second part of this talk, conformal invariance, and in the way we were able to redo many of these old theorems. So now this phase transition part, it can be summarized in 10 pages. So I will try to do it here. So it's mostly Duminil-Coupin and Vincent Tassion, also Vincent Bifara and myself. So the first thing is what's called Russo-Seymour-Welsh theory. And the first observation you make is that if there is some shape, for example, 1/2 shape, and you know you can bound the probability of crossing it, then you can bound probability of crossing shape 1/10. Or in this picture, it's 1/4. So the shape 1 by 4 can be covered by 13 overlapping shapes 1 by 2, but of smaller size. And probability that there is a crossing left to right of the big one is at least probability that there is crossing of each of those small ones. And since they are positively correlated, it's just the probability of crossing of one of this shape taken to the power 13. So if we have bound for this, we can bound that, we can get crossings of arbitrary long shapes, of annual, or whatever you wish. So the only trick is that this is a very interesting thing, but we have a symmetric shape, a square, to start with. And this only works if you have something which is a bit longer than a square. And that's the tricky part, and here is an example how to do it. Again, it's a modern rereading of the older papers. Suppose that you have some shape, not necessarily elongated, here it's even thin, and you know that A is the probability of crossing it. Then probability of crossing double that shape is at least a square over 16. And no matter what is the size of the lattice, and then you can start from a square from a square, where probability is 1/2, and then it means that for arbitrary long shape, you get some bound on the probability of crossing it at criticality. So how do you do it? So what you do is first probability to cross left part is A. Now we push this crossing down. We choose the bottommost crossing. And the bottommost crossing, it only depends on the space below. So we can resample the space above. We can play it with it as we wish. So to play it as we wish, we just make an imaginary copy of this one, a mirror copy, and that creates a symmetric shape. So there is a symmetry between blue parts and red parts. And since it's symmetric, probability of having crossing between blue parts is the same as probability of having a crossing between red parts, so it's 1/2. So it means that probability that there is this crossing is A, probability to add this is 1/2, so probability of such a picture is A over 2. Now this picture can be realized in two ways. We can either land on the top or land on the right. At least one of them should be A over 4, if the total is A over 2. Now if we land on the right, probability is at least A over 4, which is bigger than A squared over 16, so we are done. If not, then we land on the top, and we play again the same game. We land on the top, but we push it up. It only depends on this area above, and there is this crossing, but then we play the mirror game. The crossing in the mirror copy also has probability at least A over 4. And combining these two, we just resample this white region. We get a crossing which first goes along this one, but then along this one. So the crossing of the total thing is at least A over 4 times A over 4, A squared over 16 probability. So it might seem now very easy, but the interesting thing is that it took a lot of energy and time of smart people to sort of dilute the proof to something very short. The original ones were rather complicated. Now, how do you deduce that there is a phase transition from this picture? Again, this is sort of a new proof, and for it I need to use something which was independently discovered by Russo and Margulis. It's called the Russo-Margulis lemma. And site is pivotal for an event X, is flipping it creates this event. Then for increasing events, derivative of probability of the X in P is equal to expected number of pivotal sites. So what is a pivotal site for a blue crossing? It means that there is a yellow site which we flip and there is a crossing. It means that before it was yellow, there was an abstraction, but then when we flip it to blue, there is a crossing. So it's the so-called four-arm event, that there is a hexagon which has two yellow arms sideways and two blue arms top and bottom. And then flipping this hexagon, it creates the crossing event. So the important thing to understand is that there might be several pivotal sites. So for example, in this picture there are at least two. If I flip left one, I will create a crossing. If I flip the right one, I will create another crossing. And the other interesting thing that Harry Keston observed, that if you can control probabilities of these four-arm events and probability of one-arm event, you can deduce all other important probabilities for percolation. So this is an example of very technical and difficult paper which we still have not diluted to some to something easily readable, and that's probably what some people should do. Now, how we prove that there is a phase transition? So we need to estimate expected number of pivotals, which is the derivative of the probability of a crossing event. First, observe that the probability to have an abstraction is, it's not at least, it's exactly 1 minus probability of having a crossing. Yeah, in particular, it's at least. Now, again, we can move abstraction as low as we can. Note that if this is the lowest yellow crossing, we cannot move it down, so it means that there are blue crossings from the bottom to it, which are preventing us moving it down. So every point can be reached by blue from below. So to get a pivotal point, it's enough to get a blue crossing above. Now, what's the probability of having a blue crossing above? Well, it's clearly at least probability of having blue crossing in the full square, because it's easier to reach this shaded region than to traverse the whole square. So probability that there is one pivotal point that we can reach by blue one point here is at least 1 minus probability of a crossing times probability of a crossing. So we estimated the probability of one pivotal point, and already we see something very interesting, that if probability of crossing is small, or probability of crossing is close to 1, our estimate is not very good. It's very small. But if probability of crossing is, say, between 0.1 and 0.9, we get a non-trivial estimate. We get something very, very, very good. Now, suppose that we have one pivotal. Let's move this to the left. The same trick. We can resample this here. And here Russo-Seymour-Welsh theory comes in, because if a box has size n, we can draw logarithm n of concentric annuli of the same shape. And each of them, with a definite probability, will have a, say, constant, will have an arm. And each of these arms would create then a new pivotal point. So the expected number of pivotal points is at least 1 minus px times constant times log n. So essentially what we proved, that the derivative of crossing event is at least 1 minus p times log n. So whenever we are not close to 0 or close to 1, the derivative has to be very large. So essentially what we proved here, and it's really all the details I gave, that this graph of the probability of crossing a box lies in such sort of zigzag shape of which 1 over log n. This is very rough, it can be improved, but this, for example, if you take n equal to 100, already you take a width 1 over log of 100, so logarithm of 100 would be something like 6, so you already get a rather small strip. Okay, so this was before we started working with the Celian conformal invariance, and it's interesting that there are still very many open questions. So one thing is that non-self-dual models, like side percolation square lattice, we don't know how to do. So a priori what we want, and there is some progress in this direction, a priori what we want, we don't want to use that PC is equal to 1/2 from some duality, but we want to use that we take P, which is critical, and then we deduce something. Now dimension 3 is really wide open, because there is no duality. So here what we had, that abstraction to a crossing was also a curve. In 3D, abstraction to a crossing is a surface. So there is duality between curves and surfaces. And there is no clear way how to use it. So of course, like whenever this is mentioned, every other talk someone suggests to use 4 dimensions and say that abstraction to 2-dimensional crossings will be 2-dimensional abstractions. And in principle, one can do that, but nothing really spectacular came out of it. But there are some good models, and there is some good work. And what I completely left out of this talk is phase transition on general graphs, like Kelly graphs of groups, which are non-planar. There can be 2 phase transitions. At one point, you get many infinite clusters, and then at another point, they all coalesce into one. So there is a conjecture of Benjamin-Schramm. Now, we have, well, that's my only paper with Adet. We have a paper which answers in the positive conjecture of Tsirleson creates what he calls a black noise. It's kind of a counterpoint to the white noise. So white noise is completely independent. Black noise in different places, it's intimately related. So it's a sort of, at first time it looks that it's a sort of rather esoteric example of weird Fock spaces, but in reality it looks like it's an interesting object also from the point of view of physicists, but which doesn't fit in the usual realm of quantum mechanics. So it's kind of you get quantum mechanical object which you can't observe with a harmonic oscillator. And also there are very, very interesting works which were started by Schramm with Christoph Garban and Gabor Petit, and they're finishing now this without him, about noise sensitivity, how percolation reacts to noise. And we had a few times used this idea that you take the lowest crossing and only depends on what is below it, but you can push it even further. You can walk and explore the percolation landscape one hexagon by one. And this is called revealment, and there are very interesting ideas there which are really underused. So to maybe add this part on a lighter note, so I said that it's usually attributed the model to Brodmann and Hammersley, but it was actually first time mentioned in the very first volume of American Mathematical Monthly in 1894. This is this problem. Actually, look what kind of problems they were giving to school children in 1894. Actually, it's a good question. Who can tell me why they were giving this problem to school children in 1894 and they no longer give them to school children? Well, I can give you a serious answer. There are actually two serious answers. Okay, well, no one knows. Okay, so, well, no one is into school education. Well, the less serious answer that it's 10 years before Henri Lebesgue thesis, where he introduced Lebesgue integral. And since Lebesgue integral, we don't need to do repeated iterated integral dx dy dz. We can integrate with respect to area. Less serious answer, because still for calculations we want to do dx dy dz, is that in 1893, I would say that about 10% of American population would graduate from high school. So more or less the last year of high school, 10% of school children now abort the last year of high school before going to university. So back then those were the only children in high school, so they were just doing university program during their last year of high school. And that was more or less the same in France or Russia or everywhere in the world. The percentage would oscillate between 5 and 20% in developed countries, but that's the reason. So it's basically like more like first year of university now. Yeah, that's actually this problem. Yeah, maybe I should have it. So it's an equal number of white and black both of equal size are thrown into the interesting thing about this, I can show this slide at the end again, that they give a wrong solution for this problem, because they only count the probability, calculate the probability of a straight crossing. And we have seen that crossings are fractal, and we'll discuss it at length. But even that they get wrong. On the positive side, they did right. This solution is not entirely satisfactory. The problem is a pretty good one, and if, say, one will, well, it's on the next page, will solve it, then he promises to publish it. Unfortunately, it took 107 years to solve it, and I don't think he was editor by that time. Okay. Now the second part, so it's physics and post-Schramm mathematics. So the first part, I was just sort of wanted to show that it's interesting that it's really interesting that as time goes by, you get better understanding of some classical things which everyone there accepted, but they were rather tedious and difficult. Now, the interesting thing was that we were all hearing from physicists about it. And physicists, they tried to understand phase transition since a very long time, and before the war there was a Landau mean field theory. And then Stuckelberg introduced the normalization group de normalisation, and then many people worked on it, and Ken Wilson got a Nobel Prize in well, some 30 years later. And essentially how it works, you take, well, originally Stuckelberg did it for the Ising model, but you take a model and you do coarse graining. You exchange every square 4 by 4, for example, for one square, say by majority rule. If there are more open sides, you put open. If there are more closed, you put closed. Obviously, you don't get bijection between these two things. There are artificial models where there is a bijection, but in real life, you don't. It is not interesting if you get a bijection, because the idea is that you should decrease the number of degrees of freedom so that it's more tractable. But there is a hand-waving argument that this transformation, it changes length and also changes the P, or the temperature in the Ising model. And then you can see this transformation is sort of one step in some big flow on a space of all percolation models. And the critical percolation, it arises as one of the fixed points of this flow. And an interesting one with some, again, we have seen these pictures in the previous talks, that there are some repelling directions, there are some, so the usual sort of saddle point. And since this is a unique point, then it should be universal and translation scale rotational invariant. And from that, physicists get that there should be interesting critical exponents. That's the difference from mean field theory, where all the scaling exponents were usually integer. So for percolation, this is an example, and what happens is that for high P you do, well, these are pictures of renormalization. For high P, you get denser and denser things when you renormalize, and in the end you get that you can traverse everything. For low P, you get less and less dense, and for critical, you get some fractal self-similar fixed point. Again, those are non-rigorous pictures. And what happened is that the next step was that physicists understood that there is something special about 2D. It happened in several steps. So they observed that Ken-Wilson's work implies scale rotation transition invariance, and then Polyakov made a leap of faith that conformal maps, they are locally scale rotation and rotations, translations, and scale change. So if it's scale rotation, translation invariant, it should be conformally invariant. Of course, for mathematicians it doesn't work, and it's easy to come up with an artificial example of model where you have these three properties but not conformal invariance. But apparently it worked, and there is a famous paper, Belavin-Polyakov-Zamolodchikov of 1984. So KPZ is Knizhnik-Polyakov-Zamolodchikov. So Belavin was, well, in parallel they wrote it the same year. And Knizhnik, it's actually an interesting story, because he was graduate student when he wrote 3 papers. All of them are like genius level, and the KPZ paper, the great Polyakov says that only Knizhnik really understood it. But unfortunately, he died out of aneurysm and subway suddenly when he was something like 24, and left us only 3 papers. So they postulate full conformal invariance. They were able to deduce many things. Cardi worked out this sort of thing which they took for granted, boundary fields, and applied it to lattice models. So I should say that for us, for mathematicians, for probabilists, well, I'm complex analyst by my first to second education, so for me conformal invariance is a very clear thing. For probabilists, there is one clear example. There is a Paul-Levy theorem he proved probably before the Second World War, but it first appeared in his course notes and in print in 1948, that Brownian motion is conformally invariant. Now, on a lattice, random walk is not conformally invariant. You apply exponential transformation, lattice is no longer lattice, so it's not well, it's a random walk on a curvilinear lattice. But where the lattice mesh is small, you can see that the two pictures look alike. So the Brownian motion is up to time change is conformally invariant. It's preserved by all conformal maps. But it's much easier to address than percolation. It's just a Markov process. And also I want to make 2 remarks that in 3 dimensions Brownian motion is not conformally invariant. Inversion doesn't preserve it. And also in 3D, conformal invariance is not a strong property, because any conformal map of any region of 3D is one of Möbius transformations. So there is only a finite dimensional group of them. In 2D, there is Riemann mapping theorem, which says that there is an infinite dimensional semi-group of conformal transformations. So if something is conformally invariant, it has really a lot of symmetries. So you can say many things about it. And for 2D CFT, there were many wonderful predictions. So one, for example, by Denis, that Hausdorff dimension of a percolation cluster is 91/48. He actually did it before Belavin-Polyakov-Zamolodchikov, so he used conformal field theory before it was introduced. He reduced it to Coulomb gas, which is conformally invariant. And Hausdorff dimension of a leftmost crossing, the one we used, is 4/3. So what does it mean? In a box 1000 by 1000, it has length 1000 to power 4/3 on average, which is 10,000. So the crossing is 10 times longer than the box. That's the reason why it's difficult to see, because it's very, very wiggly. So if you have supercritical CT, you can drive almost in a straight line. If you have subcritical, you can drive at all. If you have critical, you drive on a fractal curve, so it takes infinite amount of time to reach your target unless your speed is very fast. And then there were critical exponents, which were, well, there are various numbers. Again, for 3D, physicists think that the situation is similar, but there are transcendental numbers without any specific meaning, without any specific nice value. But they were in 2D, they had wonderful predictions, and at the time when Adet was starting on it, we only had Keston's theorem, which proved relations between them and said that it's enough to calculate number for 4-arm exponent, for 1-arm exponent, then you can reduce all the others, which eventually we did with Wendelin. In 3D, those are numerical. Now, what started Adet Schramm's interested in this? It's a paper of Langwitz, Puyot, and Saint-Aubin, which followed earlier papers of Robert Langdon's, and it shows how important it could be to publish a paper which has no theorems whatsoever, but interesting questions. It's very difficult. Journals won't accept it, well, unless you are the famous Robert Langwitz. So he studied numerically what is the probability of percolation crossings for various shapes. And he checked that numerically there is a scaling limit. It's universal. It's independent of the lattice you use, if you use PC. And it's conformally invariant. It's a conformally invariant function of a shape. This was suggested by Eisenman. And this is like 80 pages of computer experiments, one beautiful conjecture. It was very widely read, interested many people. And then John Cardy heard about it from Eisenman, and he just wrote a formula. So this is the formula of probability of a crossing. If we believe in, well, it's not on a finite lattice. On a finite lattice, it's some polynomial in P, well, polynomial in 1/2. In this case, it's in the limit when mesh of the lattice goes to 0. And since it's conformally invariant, what Riemann tells us? It tells us that any domain can be mapped to a disk. Now we have 4 boundary points. Well, let's map not to a disk. Let's map it to a half plane. And 3 out of 4 boundary points we can map by Möbius transformation to 0, 1, and infinity. And the 4th one will be mapped to M, which is the conformal modulus. So this is the answer which John Cardy got. So he's a physicist, so it's not a proof, it's a derivation, meaning that it's a convincing, so he makes a few leap of faith, and then there is a convincing explanation why it should be so. And what he did, he moved Z on the boundary, which changed M, and he deduced, he observed that both this probability and its derivative in M have some physical meaning and can be related by a Riccati equation. And then it's the simplest equation which doesn't have an integrable solution. So it's the simplest function which doesn't have a name, so its name is hypergeometric function. So it's basically the first one after sine, cosine, and exponential. So it's not as ugly. It's basically it's an integral of some polynomial of degree 2/3. So that's. And then Leonard Carlson, who is a complex analyst, well, the greatest ever complex analyst, certainly the greatest living complex analyst, he immediately saw that, well, this is also a Schwarz-Christoffel formula for a mapping. And 1/3, 2/3, 4/3 are slopes of the angles of the polygon. So it's a mapping to an equilateral triangle. And then it says that probability of crossing in an equilateral triangle of size 1 between arc of length L and one side tends exactly to this length L. And that showed also that it's sort of, we really like a simple formula. When people saw this, many more people got interested, including, well, Adet and myself. And so I spent time trying to prove it, which eventually I did. Adet took a more sort of systematic approach. He said, well, okay, we prove it, so what? How do we describe percolation afterwards? Not clear. Let's think how to describe this picture. Well, this picture is a random coloring of a plane. It's too difficult. Well, in the end, we, together with him, managed to do it in some rather satisfactory way. But let's look at something simpler. And this is a picture from his talk 20 years ago, first talk he gave about it. I still regret that I missed that conference because I think I was too lazy. It was in Tennessee. I was too lazy to go, and it was about circle pancakes, and I knew his work about circle pancakes very well. And then a couple of my friends went and brought a Xerox copy of his transparencies. And said, wow, look at the last talk. There is something you like. He spoke about Lovely Revolution and with a random driving force. And then I said, well, like Makarov many years later, what a stupid thing, Lovely Revolution with a random driving force. I still regret that I said that it's a stupid thing, and it took me 2 additional years to start reading about that. And it's a beautiful idea. So you don't describe the full picture, you describe just this interface. It's a myopic ant who goes along using left-hand rule between gray and white, as on this picture, or between blue and yellow on my picture. And it's a random broken line, and then you pass to a scaling limit. It's a random curve. If you believe physicists, it's a conformally invariant curve. Also, it has a sort of Markov property that it doesn't look at its past. So this is how this ant looks the world. To explore it, it only needs to know the immediate neighborhood. He doesn't need to know what is in the gray area. He needs only to know this white and black. So suppose we open this slit we have drawn by conformal mapping GT, and there is a famous Lovner equation which says that this GT is a solution of this differential equation in time, which only has one parameter. And if you have this one parameter, then you can solve this nonlinear equation. Usually it's impossible to solve because it's nonlinear, non-integrable. But then you get GT, and the other way around. So you should imagine it like that suppose you are driving with a constant speed in a car. If you know how you turn your steering wheel, then you can reconstruct the trajectory of the car. Only you need to solve an equation, which is non-trivial. So here you drive a car in hyperbolic geometry, so it's less trivial even than for the usual plenary Euclidean car. And you drive with a constant speed of 2 hyperbolic miles per Euclidean hour. So what Schramm SLE is that you plug in a random steering wheel position, and then you get a random curve. And you plug in Brownian motion with a speed kappa, and of course, the bigger the kappa, the more you jerk the steering wheel, the more fractal curve you get. And the various fractal properties can be calculated using eta calculus. So the lemma which Schramm proved and presented in this talk was that if you believe physicists and some interface percolation or easing or whatever has a conformally invariant scaling limit, it has to be a SLE kappa. Now, let me just show the proof of Schramm's lemma. So let's draw the slit. Let's stop at epsilon capacity increments, whatever that means, it's electrostatic capacity, and open one by one. And there are these maps, red G epsilon, green G epsilon, blue G epsilon, and each of them we expand at infinity, z plus constant plus 2 epsilon over z. So capacity is this coefficient here. That's the definition of capacity plus small order terms. And if we compose these maps to get the map at time n epsilon, which is z plus w n epsilon plus 2 n epsilon over z plus and so on, then we get, there is a very nice property of these maps, you can view them as formal power series, that the first coefficient and the second coefficient are additive. Well, this coefficient additive is just capacity is additive, everything is okay. But this, it means that this driving force, the position of steering wheel at time n epsilon, is just sum of positions at time, sum of increments at time epsilon, 2 epsilon, 3 epsilon. And if we believe physicists that it's conformally invariant, each of this map is a random map with the same distribution, we get that the position of steering wheel at time n epsilon is a sum of independent, identically distributed increments. So it's a Brownian motion. So in a sense, SLE is a Brownian motion or random walk, if you wish, on the moduli space. In this case, moduli space is trivial because you have a half plane, you have 2 fixed points, an element of metric in one of them, so it's rather easy. But in general, you can do it on any Riemann surface, only then the moduli will be more difficult. Well, this is the proof without this discretization, but indeed the proof is very easy. It's very nice, and you get very nice fractal curves. For example, when kappa is smaller than 4, they are almost surely simpler. Between 4 and 8, they almost surely touch themselves. At kappa bigger than 8, they are piano curves which cover the whole plane without self-intersecting. And then Before calculated its dimension, and there are nice dualities. The question is, of course, how is it related to percolation? And why there is conformal invariance built into a lattice. It's more or less like one can see it for random walk. It's not the usual proof, but it's one of the possible proofs, is that Brownian motion is related to harmonic and analytic functions, and random walk is related to discrete harmonic, discrete analytic functions. So it turns out that instead of moving point Z on the boundary like Cardi did, we can move it inside. And then look at the probabilities of events. For example, HA of Z is probability that Z and A are separated by blue arc from C and B. What at that time I did, I proved that these functions HA, B, HZ are approximately discrete harmonic, conjugate to each other, and some boundary conditions gave us the Cardi's formula. So the interesting thing is that I always feel a bit dissatisfied with this proof, because for complex analysts it looks rather easy, but then people ask some weird questions and I have to explain why a priori estimates are trivial. And my advisor tells that I shouldn't talk to people who don't understand that they are trivial. So what happened is now we simplified it. And it's actually, I sent my graduate student proving it, go fishing for the conformal invariance on square lattice. Instead, he trivialized my proof for the hexagonal lattice. Well, still it's a good thing. So what we do, first we work rather not with percolation, but with O1 model. So there is a bijection between percolation and loop configurations. So you see that there is the same number of loop configurations as coverings in two covers. Because once I have a loop configuration and I start at some point covering, then there is only one way to cover it. So there is a factor of 2. I have to fix one hexagon, but then it's very easy. And then there is also a nice observation that the blue top-bottom crossing is the same for O1 model as this picture. And yellow crossing is the same as the picture, the opposite one. So it's like tennis balls two ways. So that was very well known. Now, what we observed, and the first thing which was observed, that apparently these functions HA, HB, and HZ, they have some meaning in terms of O of n model. In a sense, if here we had two curves, we have many loops, but also curves starting at A, Z, B, and C. Here we also have many curves, but we also start with many loops, but we start curves at C, B, A, and Z. And there are 3 different ways to connect C, A, B, and Z. Let's say I thought I have, so those are 3 different ways. And the partition functions for these 3 different ways are exactly HA, HB, and HC. Now, well, there is a proof. The proof is more or less the same as the proof here that you recover. Only here, strictly speaking, what you need to do, you need to prove to move blue crossing as close as possible to C and B. Then it depends only on the thing on the right. And then you have to resample this thing so that A is connected to Z. So it's kind of interesting, because this picture cannot be covered blue and yellow. It just can't be covered blue and yellow, because there is this disorder operator, as physicists would say, at Z. It's kind of a point in space, so that if you walk around this point in space, blue becomes yellow and yellow becomes blue. So you get kind of a negative of the world. But then if you walk around the second time, then again yellow is yellow and blue is blue. So it's not important for the purposes of the proof, but it's a nice observation that this is HA. Now, this implies actually that HA plus HB plus HC equal to 1. Because you just calculate partition function, normalized partition function to be 1 when you have 4 sources at A, B, C, and Z. And then there are 3 ways to connect them. So these 3 ways, they sum up to 1. Now, we already found something conformally invariant. We have found a function which is identically 1. Identical 1 function is conformally invariant, but it's trivial, so it's not interesting. Now, we want to find a function f which say defined on the edges, and for every 3 adjacent edges, it has this property that the sum of f at 3 edges multiplied by 3 cube roots of unity is equal to 0. Why? Because this is exactly the discrete contour sum along this contour, because if this vector is I, this is I times tau, and this is I times tau squared. So these 3 vectors, they are proportional to cube roots of unity times I. And if you add this relation for a number of neighboring triangles, then these 2 edges cancel out, these 2 edges cancel out, these 2 edges cancel out. So you end up with a contour integral being equal to 0. You can pass to a limit, and you deduce that if your functions have limits, then the limits have contour integral 0, and they are analytic. Now, knowing that this is equal to 1, let's take the next symmetric sum of them with coefficients cube roots of unity. So it turns out that they satisfy the discrete Cauchy-Riemann relations. And the difference from the original proof is that for some misguided reasons, in the original proof we were considering these functions at vertices. And at vertices you don't have these nice properties because there are 3 edges emanating from a vertex. So you can have 3 curves joining to a vertex. But if you consider them at an edge, there is a nice XOR argument which tells that there is this equation. And basically, if you have a curve which arrives here and the site is empty, you can always continue it by train tracks left to right. So such configurations, this triplet contributes 1 to every of 3 terms. So you get 1 plus tau squared equal to 0. If it's this picture, again it's 1, 1, 1, you change the train tracks. And then there is an interesting picture when you touch not a loop, but you touch connection between C and B. And then when you change train tracks, you contribute 1 tau and tau squared, because those were coefficients in front of H. And then you get the identity 1 times 1 plus tau times tau plus tau squared times tau squared, again equal to 0 because it's a cube root of unity. So it's a simple game with train tracks XOR. It's indeed the whole proof. So it gives you this trivial Cauchy-Riemann, and then you can pass to a limit, and you get that their functions, this function is homomorphic in the limit. Now I have 2 more minutes to give you the boundary values. Now, what are the boundary values? Suppose that Z lands on an arc AB. Well, this picture is possible, HA. This picture is possible, HB. But the picture HC is not possible, because then these 2 curves would intersect. So when we land on the arc AB, this term is not possible. So it's a convex sum of 1 and tau. So for the arc AB, f of z belongs to 1 and to interval from 1 to tau. So it means that our thing is a homomorphic function inside, but also it maps AB to interval 1 tau, BC to interval tau squared, AC to the interval tau squared 1. So you get a homomorphic function which takes domain with 3 marked points to an equilateral triangle. Well, by argument principle, it's exactly the conformal map. So the only difficult point which I left under the carpet is the Russo-Seymour-Welsh estimates, but the first half says that they are easy. From this, you can actually deduce the SLE6. This is a calculation, but I don't have time for that. It's really not a difficult argument. So what are the open questions? Well, do other than hexagonal lattice, even other self-dual models we can do. Something in 3D. There is some progress, chiefly now with Ising model by Michael Eisenman, Hugo Dominiou-Copan, and Vladas Sidarevičius. Also, it would be interesting to do experiments without SLE that we can do for Ising. Also, thing which independently I did, and I thought for a very long time, and we only started thinking about it together when he died, how to deduce everything from locality. Just locality of percolation is not enough, because stretched percolation is local but not conformally invariant. But some symmetry should do the job, and do renormalization rigorously. And maybe my most favorite is the high temperature Ising and SLE6. If you do renormalization for the Ising model, then there is a critical Curie temperature which we can do. It's another fractal SLE3. Low temperatures, Pfister and Vilnik have shown that everything trivializes, but all the high temperature Isings, they should converge in terms of spin correlations to trivial, something trivial like white noise if you normalize, but in terms of connections, they should converge to percolation. And that's wide open. Thank you for your attention. Can I have 3 more minutes non-math? Yeah. Sorry? Yeah, I want to speak 3 more minutes.
We have time for only one question, and I'm going to give it. Stas, what would you like to say in the next 3 minutes?
Well, okay, now my pointer doesn't work. Everyone says that the first ICM was in 1897 in Zurich, but actually I don't know how many people know that there is mathematicians, especially French one, like to number natural numbers from 0, that the first one actually was here in Chicago and Evanston in 1893. Who knows that? Okay, so no one has been there, no wonder. So St. Petersburg is picking up the next one, which is 3 years' time, exactly 3 years to the date. I was, when preparing, I was sort of looking, and it's a very funny thing. I saw a week ago in St. Petersburg Philharmonics that they already had a major statistical gathering in 1872. Opening of the 8th International Statistical Congress. Well, that's not a Bernoulli Society meeting, it's the statisticians who discuss how they should count barrels of whiskey or things like that, normalizing different counts, but still I find it's you can almost imagine that it's our meeting. So ICM will be in 2022, July 6 to 14, because the weather is nice in St. Petersburg at that time, and also some countries asked to move it earlier. Now, it's a beautiful city. It's very welcoming. It was built as a window of Russia to other countries, and we'll be very happy to see everyone. And in particular, the entry will be visa-free. So it was tried for 850,000 people during the World Cup. Now it's an easier job for 5,000 people. But basically, when you register for ICM, you can print out at home a paper with a barcode, which works as a visa at the entrance. Oh, well, of course, we will screen for football hooligans, and you know that during the World Cup, they actually apprehended 5 narco dealers from Mexico traveling under assumed names. So, the other thing we want to try, we secured private funding to, well, there is the usual thing about supporting developing countries, but to support 1,300 or more younger mathematicians. So we'll try to work with our colleagues from IMS, and national math societies in Europe to somehow distribute these grants, and we'll hope it work. And we'll need your help. And the ICM side went up the day before yesterday, or maybe no, wait a second, today. Well, 5 days ago. So please visit it if you have some ideas how to make this thing better. We'll be very, very happy to hear them. Well, that's the website. So hope to see you in 3 years' time in St. Petersburg.
So we are now going into the coffee break, which is upstairs, and then we will be going into invited and contributed sessions. Most of the rooms for those are on the second floor, the same room as the coffee. And then after that this afternoon, the reception is about a 5-minute walk outside. Either look at the map in what you were given or follow some people who look like they know where they're going. And let us thank Stas again for a beautiful talk.